Okay, so you've got this idea of torque now, that the torque is a turning force or turning effect. It's created by having a force being applied at a particular position around a fulcrum so that it actually can get a rotation going for an object. So it could be a door being pushed around. Don't forget that a bigger force will give you a bigger torque. The torque is proportional to the force. And if you go to a larger distance from the fulcrum and apply that force, especially at 90 degrees, you're going to get your maximum, you get a very big torque. So as a combination, you get torque as force times distance, and that applies to things like spanners trying to turn nuts. The longer you can make that handle, the more torque you're going to get out of that tool. So some of the questions you'll see on your worksheet are all about finding an unknown part of the torque. So if you're told we've got a balancing act here going on, and where would you place this 300 gram mass to give you an equal torque so it stayed balanced, you would actually want to get a torque that's going to the right here, being generated by the 100 gram mass 60 centimetres away. That's going to give you one sort of torque. That torque should equal here if it's going to be balanced. So you can make that statement that the torque on the left is the same as the torque on the right. And torque, don't forget, is force times by distance to that fulcrum position. So this left-hand side here, you've got a 300 gram force there being applied at a distance we don't know, so I'll probably do that as dl at the moment. On the other side, you've got a force of 100 grams and a distance of 60. So we can actually work out that torque on the right straight away as 6,000. So for this to be balanced, this torque here has to be the same. So you're really just solving this equation here and trying to find out what dl is. So dl is being times by 300. To get rid of the times by 300, we would divide by 300 there, and you would get, sorry, that's 6,000 there, so it would be 20 centimetres. Okay, so when you're doing that, that gives you a simple way of actually solving it. You would do the same sort of thing here with this one. So in this lower one, you've actually got the same sort of thing going on, but the unknown is actually a force in this case. You're still sort of saying that the left hand and the right hand torque should be matching, but this time it's the force times the distance here generated by the left, force times distance on the right. But this is the force that's the unknown. We don't actually know that this time, rather than a distance. It's times by 10 centimetres. On the right, you've got 100 grams generating some force due to weight, and you've also got 24 as a distance between the centre of the weight and the actual fulcrum. So again, you can work out one of these torques straight away. And all you're really doing in here is actually solving what's going on. So we're trying to get rid of this FL times by 10. We would do FL is going to be the other side divided by 10. And you end up with 240. That doesn't seem right. No, so it's grams. 240 grams. So that's actually the mass of the rock there, based on that. So if you look at that, that would be the unknown here. And that was one of the things you did in the practical. As well, just give them one mass. So if you're just giving materials a 1 metre ruler, or an object there, 1 metre ruler, one known weight of 50 grams, and some sort of a fulcrum, that's all you would need with torque to find out the mass of the ruler. So what you would do here, you'd have the ruler there, you would put your fulcrum offset somewhere, so say at the 30 centimetre mark, something like that. Alright, now that would mean that if it's a balanced ruler there, that the centre of gravity of the ruler would be at the 50 centimetre mark. Because if you were to hold the ruler up and grab around the 50 centimetre mark there, it should actually balance on your finger. Okay, so that's your centre of gravity. That's where your average position of the weight is for that ruler. So on that side there, right, this is where your force is going to be acting. Okay, so your force is acting down through there, through that position there. Now that means you know that you've got this at 20 centimetres away. Alright? Now all you really need to do there then is actually sort of slide your 50 gram mass along here and actually try and find a position there where that 50 gram mass actually balances the torque on the other side. Because again, if you look at torques, the torque on the left hand side is going to be balanced by the torque on the right hand side generated by the ruler. So again, it's force and distance on one side, force and distance on another. On the right hand side here, we've got the unknown ruler weight there. We know that we placed it 20 centimetres away from the fulcrum. On the other side here, we've got a 50 gram mass. And all we really need to do is find out how far is it from the centre of that fulcrum to the centre of gravity of that. So we move this along side to side. until the actual things become balanced, and then you actually record that in there. So if you do that on here, I'll do that on mine, and I'll try and show you this later on. Doing that on the 30 mark, putting it on the other side here, and it balances there on the... So what I've got there is 4 centimetres. That means that distance in here is 26 centimetres. Okay, so to solve that there, you do 26 times 50 there. So just at the side here, 26 5s. 5 6 is 30. 5 3 2 is 10. Plus 3 is 13. So you're going to get 1300 there. With the 0 to come. Equals f times by 20. So the f will be the 1300 divided by 20. 100 divided by 20, which is 65 grams. And you can then check that in the electric balance and see if it actually matches up. Okay, thanks.